Hello and welcome back to A-Level Geography Explained. In this video, we'll be exploring the first inquiry question of the water cycle topic. We'll cover key areas, the global hydrological cycle, drainage basins as open systems, and how the hydrological cycle influences water budgets and river regimes at a local scale. As always, these videos should be viewed as part of your wider revision. Let's begin. The global hydrological cycle, or water cycle, is a closed system. This means that water doesn't enter or leave the cycle, it simply moves between different stores within the Earth. It works through continuous processes driven by two key types of energy, solar energy and gravitational potential energy. Solar energy drives evaporation, where water changes from liquid to vapor and rises into the atmosphere. This process is fundamental because it powers much of the water cycle, particularly the movement of water into the atmosphere from oceans, lakes, and rivers. Gravitational potential energy moves water through the system. This comes into play when water falls as precipitation or flows through rivers and lakes. Gravity is essential for moving water from higher to lower areas, such as when water moves down a slope or falls as rain. The water within the cycle moves between various key stores. These stores hold water for different amounts of time, and understanding them is critical. 1. Oceans. By far the largest store of water on Earth, oceans contain around 97% of all the water on the planet. However, most of this water is saline, meaning it's not directly usable by humans. 2. Atmosphere. Water in the atmosphere exists primarily as vapor, playing a key role in precipitation and cloud formation. The atmosphere contains a small but critical amount of water, essential for local weather patterns and the overall cycle. 3. Cryosphere. This store includes frozen water in the form of glacier, ice caps, and sea ice. It has a long residence time, meaning the water is locked in ice for thousands of years before it becomes active again in the cycle. Because of climate change, the cryosphere has become an area of great concern, as melting ice contributes to sea level rise. 4. Biosphere. Water is stored in living organisms, from plants and animals to microorganisms. The process of transpiration is key here, where plants release water vapor into the atmosphere, affecting local climates and water cycles. 5. Surface water. This refers to water stored in rivers, lakes, and reservoirs. It's important for human use, agriculture, and ecosystems, although it makes up a small fraction of the total water on Earth. 6. Groundwater. Water stored in aquifers beneath the Earth's surface. It is a crucial source of fresh water for drinking and irrigation, particularly during dry periods. Groundwater often moves slowly, which makes it a more reliable source of water, although some aquifers are considered non-renewable on human timescales. Water fluxes are the processes that move water between these stores. Understanding these is essential. Evaporation, water changing from liquid to vapor, particularly from oceans, rivers, and lakes. Precipitation, water returning to the Earth's surface as rain, snow, or hail. Infiltration, water moving from the surface into the soil. Transpiration, water released from plants into the atmosphere. Runoff, water flowing over the surface, often into rivers and eventually the sea. Some stores, like fossil groundwater and ice, are considered non-renewable because the time it takes to replenish these stores far exceeds human timescales. Fossil groundwater, for instance, can take millennia to accumulate. Now, let's turn our attention to drainage basins. Unlike the global hydrological cycle, a drainage basin is an open system. Water enters the basin through precipitation and leaves it through river discharge, evaporation, or transpiration. Within a drainage basin, there are several key processes happening. The main input is precipitation, although snowmelt and surface water entering from other areas can also add to the basin's water supply. Water moves through the basin via several key pathways. Interception, vegetation intercepts rainfall, preventing immediate surface contact. Infiltration, water soaking into the soil. the permeability of the soil affects how much water can infiltrate. Direct runoff: when rainfall exceeds the soil's capacity to absorb it, water flows over the surface and into streams or rivers. Through flow: water moving sideways through the soil, towards rivers. Percolation: water moving deeper into the soil or rock layers, eventually becoming groundwater. Groundwater flow: water moving horizontally beneath the surface, feeding into rivers or lakes. Outputs: water leaves the basin through. Evaporation: water returns to the atmosphere from lakes, rivers, and other water bodies. Transpiration: water released by plants into the air. River discharge: water flowing from the drainage basin, eventually making its way to the sea. The characteristics of a drainage basin are influenced by several physical factors. Climate: the amount and type of precipitation, rain, snow, etc., and temperature affect how much water enters the system. For instance, tropical climates may have year-round rain, whereas temperate zones have more seasonal rainfall. Soils: the permeability of soils dictates how much water infiltrates and how quickly runoff occurs. Sandy soils, for example, allow more water to infiltrate than clay soils. Vegetation: plants can intercept rainfall and transpire water back into the atmosphere, impacting how much water reaches the ground. Dense vegetation tends to reduce runoff. Geology: permeable rocks like sandstone allow more infiltration, while impermeable rocks like clay prevent water from soaking in. Relief: steeper slopes lead to faster runoff, whereas flatter land allows more infiltration and less immediate runoff. Human activities, like deforestation, urbanization, and the construction of dams, can significantly alter a drainage basin's characteristics. For example, deforestation reduces interception, leading to increased surface runoff and a greater risk of flooding. Urbanization, with its impermeable surfaces, accelerates runoff and contributes to flash floods. A famous example of human impact on a drainage basin is the Amazon basin. Here, large-scale deforestation has altered natural water flow, changed precipitation patterns, and impacted the water cycle both locally and globally. Water enters the drainage basin by precipitation. Here are the three main types of rainfall. Relief rainfall occurs when moist air is forced upwards by a mountain range or other elevated terrain, resulting in cooling and condensation, leading to precipitation. Frontal rainfall occurs along the boundaries of two air masses with different temperatures and densities. These air masses, separated by a front, interact, forcing one air mass to rise over the other. This rising air cools, leading to condensation and the formation of clouds and rain. Convectional rainfall occurs when warm, moist air rises, cools, and condenses, leading to the formation of clouds and precipitation, often in the form of heavy showers or thunderstorms. Moving on to water budgets, a water budget is the balance between inputs and outputs in a given area. This balance determines how much water is available for use, especially in agriculture, industry, and daily living. A positive water budget occurs when inputs exceed outputs, leading to a water surplus. This situation is beneficial for agriculture, where excess water supports crops. On the other hand, a negative water budget happens when outputs surpass inputs, leading to water deficits. This is often associated with drought conditions. Climate significantly impacts the water budget. Tropical regions often have a water surplus due to consistent rainfall, which supports abundant water availability throughout the year. Temperate regions tend to have seasonal variation in their water budgets, with a surplus in winter and a deficit in summer. Polar regions, where precipitation is low and temperatures are cold, often experience a negative water budget, particularly during the winter months. The soil water budget describes the balance between inputs and outputs from the soil. This varies seasonally. Surplus is when precipitation is greater than evapotranspiration. Deficit is when evapotranspiration is greater than precipitation. Field capacity is when soil is fully saturated after rainfall. Soil moisture recharge is the refilling of soil stores after a dry period. This is important for understanding river regimes, droughts, and agricultural planning. Lastly, let's look at river regimes, which describe how river discharge changes over the year. Different rivers follow different discharge patterns, depending on their location and climate. Key factors influencing river regimes include rainfall patterns. Seasonal rain leads to seasonal peaks. Snowmelt. Rivers fed by snow show peaks in spring and summer. Glacial melt. Rivers like the Indus show dual peaks, from snowmelt and from monsoon rainfall. Basin geology and soil. Permeable rocks moderate flow, impermeable surfaces increase peaks. Different rivers around the world demonstrate different regime types depending on these conditions. Examples of river regimes are the Amazon River, which has high flows in the wet season due to heavy rainfall. The Yukon River peaks in early summer as snow melts in Alaska. The Indus River shows high discharge from glacial melt in early summer and again with the South Asian monsoon. Understanding river regimes helps predict flooding and manage water supply. Finally, we will look at storm hydrographs. A storm hydrograph shows how a river's discharge changes in response to a rainfall event. Hydrographs can be described as either flashy, quick response, or delayed, slower response. Let's take a look at this storm hydrograph, a powerful tool used to understand how a river responds to a rainfall event over time. Along the bottom, we have time in hours. On the left, the blue bars show rainfall in millimeters, and on the right, the orange line with diamonds shows river discharge, or how much water is flowing through the river, measured in cubic meters per second, or cumics. Now, let's walk through what happens during and after a storm. The first thing we see is peak rainfall, where the heaviest rain falls. This is shown by the tallest blue bar, occurring around hour 18. After that, the orange discharge line begins to rise. This upward curve is called the rising limb. It shows how quickly the river starts to fill up with water from rainfall. Water moves over the land as overland flow, and also through the soil as through flow, eventually reaching the river. The highest point on the orange line is called the peak discharge. This is when the river is carrying the most water. If the discharge goes above the bankfall level, marked by the dashed black line, the river could overflow and cause flooding. But here's something important to notice: the lag time. This is the delay between the peak rainfall and the peak discharge. It happens because rain doesn't enter the river instantly. It has to travel across the land or through the soil first. After the peak, the river starts to empty, and the line begins to fall. This downward curve is called the receding limb or falling limb, as the river returns to normal flow. Finally, we have the base flow, the light orange dashed line. This is the normal day-to-day flow of the river, mostly fed by groundwater and unaffected by recent rain. When we look at storm hydrographs, we often classify them as either flashy or delayed. A flashy hydrograph has a short lag time, a steep rising limb, and a high peak discharge. This means the river responds quickly to rainfall, often leading to a higher flood risk. Flashy hydrographs are typical in smaller drainage basins, steep relief areas, or where the ground is impermeable, like urban areas with lots of concrete. In contrast, a delayed hydrograph shows a longer lag time, a gentler rising limb, and a lower peak discharge. Here, the river responds much more slowly to rainfall, meaning there's less immediate flood risk. Delayed hydrographs are common in larger basins, flatter landscapes, or areas with permeable soils where water infiltrates easily. Physical factors affecting hydrographs include: small, steep basins produce faster responses. Impermeable rock and soil prevent infiltration, increasing runoff. Sparse vegetation leads to quicker runoff and higher peaks. And dense drainage networks deliver water to the river faster. Finally, human factors affecting hydrographs. Urbanization leads to flashy hydrographs because impermeable surfaces increase surface runoff. Planners manage these impacts by introducing flood defenses, land use zoning, and sustainable drainage systems like green roofs and permeable pavements. Hello and welcome back to A-Level Geography Explained. In this video, we'll be exploring the second inquiry question of the water cycle topic. The parts covered in this video are how deficits and surpluses in the hydrological cycle have significant impacts, and how climate change may have significant impacts on the hydrological cycle, both globally and locally. Let's begin. A hydrological deficit occurs when there is a shortfall in water supply due to a lack of precipitation or high evaporation rates. These deficits are typically linked to physical processes such as weather patterns and climate cycles, but they can also be significantly exacerbated by human activities. Let's look at the causes of drought. Droughts can be caused by both meteorological and hydrological factors. Meteorological drought occurs when there is a significant deficit in precipitation over a short period. This typically happens during dry seasons or as a result of weather systems that block rainfall. For example, in regions like Australia, prolonged dry spells are common due to natural climatic variability. A hydrological drought, on the other hand, is more about the impacts on water availability in rivers, lakes, and groundwater systems. This type of drought can occur even if precipitation levels are normal, due to increased evaporation or inefficient water storage systems. One key factor influencing both types of drought is the El Niño Southern Oscillation. ENSO alternates between two phases, El Niño, a warm phase, and La Niña, a cold phase. El Niño is characterized by the warming of the surface waters in the central and eastern Pacific Ocean. This warming disrupts typical weather patterns, often leading to drought in regions like Australia and the Sahel, where rainfall is significantly reduced. La Niña, on the other hand, refers to the cooling of those same Pacific Ocean waters. This cooling generally leads to the opposite effect, increasing rainfall in places like Southeast Asia and Australia, while sometimes intensifying droughts in other regions such as the western coast of South America. Both phases can last several months to over a year and have significant global impacts, including alterations to the hydrological cycle, which may exacerbate drought conditions in certain regions or trigger intense rainfall and flooding in others. While droughts themselves are driven by natural processes, human activity can make them worse. One of the major ways this happens is through the over-abstraction of water resources. In regions like the Sahel or Australia, human use of surface water and groundwater has severely depleted water reserves, making drought conditions even more severe when they occur. Over-abstraction can reduce the water available to ecosystems and increase competition for limited water supplies. Another human contribution is deforestation. When forests are cleared for agriculture or urban development, the local climate can become drier, and the natural processes that regulate the water cycle, such as transpiration, can be disrupted, exacerbating drought conditions. Droughts have significant impacts on ecosystems. In areas where freshwater resources are scarce, wetlands and forests are particularly vulnerable. For instance, the Pantanal, a vast wetland in Brazil, has suffered severe damage due to prolonged droughts, which reduce water availability and disrupt the habitats of various species. Similarly, forest stress is another consequence of drought. In regions like the Amazon, droughts weaken tree health, making them more susceptible to disease and pests. This can cause a loss of biodiversity and further destabilize the ecosystem. While some ecosystems are more resilient than others, prolonged drought can push them past their tipping point, resulting in irreversible damage. Surpluses within the hydrological cycle can lead to flooding, with significant impacts for people. When water levels in the hydrological cycle exceed normal levels, flooding can occur. Surpluses in the system typically happen after periods of intense rainfall, snowmelt, or prolonged wet conditions. Let's look at meteorological causes of flooding. Flooding is commonly caused by intense storms or heavy rainfall. In the UK, depressions and low-pressure systems bring heavy rain, which, when combined with saturated ground, can lead to flash flooding. These types of floods occur rapidly and can be highly destructive. Monsoonal rainfall in countries like India or Bangladesh also contributes to flooding, particularly during the rainy season. Similarly, snowmelt can contribute to river flooding when warm temperatures cause snow to melt quickly, overwhelming river systems. Each of these causes involves sudden, intense surpluses of water, and when the ground is already saturated, it's difficult for the excess water to be absorbed, leading to flooding. Human activities are a significant contributor to increased flood risk. Urbanization is one of the main drivers. As cities grow, large areas of land are covered with impermeable surfaces like concrete, which prevent water from infiltrating the ground. This increases surface runoff, leading to flash flooding during heavy rainfall events. In addition, poor river management can exacerbate flooding. Over-reliance on hard engineering solutions, such as levees and dams, can sometimes increase flood risk. For example, the construction of dams might trap water, and when the dam fails or is overwhelmed, the resulting flood can be catastrophic. Furthermore, the practice of draining wetlands or altering river courses to facilitate urban development often reduces the land's natural ability to absorb excess water, increasing flood severity. Flooding doesn't just have immediate impacts on people and infrastructure, it also has lasting environmental effects. For instance, soil erosion and waterlogging can degrade agricultural land, reducing its ability to support crops. Floodwaters can also lead to the destruction of wetland ecosystems, which serve as critical habitats for wildlife and play a role in water filtration. The socio-economic impacts of flooding are also significant. Beyond the loss of life, floods can cause widespread economic damage. Businesses and homes can be destroyed, leading to disruptions in local economies. Infrastructure such as roads, bridges, and power lines can be severely damaged, complicating recovery efforts. Settlement patterns can also be affected as people are displaced, leading to long-term challenges for affected communities. In the UK, floods like those from Storm Desmond in 2015 had both short-term and long-term impacts on people's lives and the economy. Climate change is having a profound effect on the hydrological cycle, both globally and locally. As the climate warms, changes in precipitation, evaporation, and water availability are becoming more apparent. As global temperatures rise, precipitation patterns are changing. Some areas are experiencing more intense rainfall events, while others, like the Sahel, are becoming drier. Changes in evaporation rates are also being observed, with higher temperatures leading to more rapid evaporation of water from lakes, rivers, and soil. This leads to drier conditions in some places and more intense storms in others, creating a cycle of unpredictability. Climate change is impacting key water stores like snow and glacier, with many regions seeing a reduction in ice mass as temperatures rise. This reduces the amount of water available for future use and increases the risk of flooding as glacier melt. Similarly, reservoirs, lakes, and permafrost are all vulnerable to warming, leading to changes in water availability and flow patterns. Soil moisture levels are also being affected, with some areas becoming drier and others experiencing more frequent and severe rainfall, affecting agricultural productivity and water supply. Stream flow and runoff rates are being altered, making some regions more prone to flooding while others are at greater risk of drought. One of the most challenging aspects of climate change is the uncertainty it brings to the hydrological cycle. While we can observe trends, the exact future impacts are difficult to predict. ENSO cycles are expected to become more intense, with the risk of severe droughts and floods increasing. Global warming is also leading to changes in weather extremes, making it harder to predict when droughts or floods will occur and how severe they will be. This uncertainty creates significant concerns for water security, as changes in precipitation and evaporation patterns can directly impact the availability of freshwater resources. The need for adaptive water management strategies is becoming increasingly urgent to address these evolving risks. The Sahel, a semi-arid region just south of the Sahara Desert, has been significantly impacted by climate change. Over the past few decades, the region has seen a marked shift in rainfall patterns, with rainfall becoming more erratic and seasonal. This has led to both prolonged droughts and intense rainfall events, creating a volatile environment for local communities who rely on consistent rainfall for agriculture. As temperatures rise, evaporation rates increase, further depleting the already limited water resources. In some years, the rains fail entirely, leading to crop failures, water shortages, and increased food insecurity. Conversely, when intense rainfall does occur, it can lead to flash floods, causing damage to infrastructure and displacing communities. The increasing unpredictability of the region's water cycle is threatening the livelihoods of millions. Climate models suggest that these trends will likely continue, which makes water security in the Sahel even more uncertain in the future. Hello and welcome back to the channel. Today we're exploring the third inquiry question of the water cycle topic: how does water insecurity occur, and why is it a global issue for the 21st century? This is a key part of the A-Level geography spec, bringing together physical and human causes, the impacts of insecurity, and different strategies to manage water resources sustainably. Let's begin. Water insecurity often begins with the physical geography of a region. One of the primary causes is climate variability. Some regions naturally experience low rainfall or suffer from extended dry seasons, while others are facing more unpredictable weather patterns as a result of climate change. For instance, the Sahel region in Africa is becoming more arid, with desertification becoming an increasingly urgent problem, which leads to water shortages and food insecurity. Prolonged droughts in places like California or Australia drastically reduce river flows, shrink lakes, and dry up reservoirs, making water availability unreliable. Geology also plays a key role in water availability. Regions with permeable rock types like sandstone or chalk allow water to infiltrate and accumulate in underground aquifers, which can provide long-term storage for water. But in contrast, areas underlain by impermeable rock like granite or clay don't allow for significant infiltration, which leads to more surface water and less groundwater storage. An example of this can be seen in parts of Africa, where the geology significantly limits groundwater access. Topography also has an impact. In mountainous regions, steep relief speeds up the rate of surface runoff, meaning less water can infiltrate the soil or replenish underground stores. This leads to a higher likelihood of floods during intense rainfall and less availability of water during dry periods. In contrast, flatter regions with low relief often have more extensive floodplains where water can spread out and be absorbed. Another major physical factor is saltwater encroachment, which is becoming more prevalent with rising sea levels. In coastal areas, excessive groundwater extraction can lower the water table, allowing seawater to seep into freshwater aquifers. This is already a serious issue in parts of Bangladesh, where saltwater intrusion is contaminating vital groundwater supplies, making them undrinkable. While physical geography plays a significant role, human activity often exacerbates water insecurity. One major factor is over-abstraction. As the global population grows and urbanization accelerates, the demand for water increases dramatically. In agricultural regions, water is often over-extracted for irrigation, particularly in countries like India, Pakistan, and the USA. For example, in the Punjab region of India, farmers have been extracting groundwater from aquifers faster than it can recharge, leading to steadily declining water tables. Pollution also contributes to water insecurity. Agricultural runoff, containing pesticides, fertilizers, and other chemicals, leads to the eutrophication of lakes and rivers, reducing water quality and harming aquatic ecosystems. In countries like China, more than half of the rivers and lakes are polluted, rendering them undrinkable. Industrial waste and untreated sewage further degrade water quality. In many low-income countries, water pollution is a leading cause of waterborne diseases, including cholera and dysentery. The rapid pace of population growth and urbanization has created a situation where the demand for water outstrips supply. Cities like Cape Town in South Africa, São Paulo in Brazil, and Mexico City are facing severe water shortages due to urban sprawl and rising demand. In these cities, water resources are being rapidly consumed, leading to both supply and infrastructure challenges. The impacts of water insecurity are far-reaching and multifaceted, affecting both individuals and nations. On a human level, limited access to clean water leads to significant public health challenges. Inadequate sanitation and unsafe drinking water are responsible for millions of deaths annually from diseases like cholera, typhoid, and dysentery, particularly in developing regions. The impact on children is particularly devastating, as waterborne diseases are one of the leading causes of death among young children in sub-Saharan Africa. Water insecurity also affects economic productivity. Agriculture, which is highly dependent on reliable water supplies, is often the first sector to suffer. For instance, during droughts in the Horn of Africa, agricultural production falls sharply, leading to higher food prices and food insecurity. Similarly, countries that depend on hydropower, like Ethiopia and Brazil, face energy shortages when water levels in reservoirs drop. On an environmental level, ecosystems are also severely impacted by water insecurity. Wetlands dry up, impacting biodiversity and carbon sequestration. Rivers, lakes, and wetlands play a critical role in supporting wildlife, and as they shrink, so does the habitat available for species. In the Aral Sea region, for example, over-extraction of water for irrigation has led to the collapse of what was once one of the world's largest lakes, resulting in the loss of fish species and harming local communities dependent on fishing. Social and political tensions are another significant impact. Water scarcity often leads to conflict between countries sharing transboundary water resources. The Nile Basin, for example, has seen increasing tensions over access to water between Egypt, Sudan, and Ethiopia. Similarly, the Jordan River has been a source of dispute in the Middle East for decades. As water becomes scarcer, nations are more likely to engage in political and diplomatic struggles over its control. To address these challenges, countries often turn to hard engineering solutions. Dams, reservoirs, and large-scale water transfer projects have been implemented to increase water storage and redistribute it where needed. The Aswan High Dam in Egypt, for example, provides water for irrigation and hydroelectric power but also has environmental and social impacts, such as the displacement of communities and changes in sediment flow downstream. Water transfer schemes are also popular, especially in countries like China, where the South-North Water Transfer Project is designed to move water from the water-rich south to the arid northern regions. However, these projects are expensive, energy-intensive, and often result in significant ecological changes in the donor regions. Desalination, the process of turning seawater into drinking water, is another high-tech solution that has been implemented in many dry countries, including Israel and Saudi Arabia. While effective, desalination is energy-intensive and expensive, making it a less viable option for poorer countries. In addition, the byproduct of desalination, saline water, is often dumped back into the ocean, where it can harm marine ecosystems. In contrast, sustainable solutions aim to manage water resources in a more eco-friendly way. Water conservation initiatives, such as promoting efficient household water use and reducing waste in agriculture, can significantly alleviate pressure on water supplies. For instance, in Israel, drip irrigation techniques allow farmers to use water more efficiently, minimizing waste while improving crop yields. In regions where rainfall is seasonal, rainwater harvesting offers a low-cost solution to collect and store water for future use. For example, in India, many rural households have started building rainwater harvesting systems, which can be used for irrigation, drinking, and domestic use. Appropriate technology is crucial in low-income areas. Simple yet effective technologies like sand dams, which capture and store water during the rainy season, are empowering communities to manage water sustainably. Similarly, rainwater catchment systems and low-cost filtration systems have been implemented in places like rural Kenya, helping to reduce the need for large-scale infrastructure projects that can be costly and difficult to maintain. Water security is shaped by multiple players at different scales. National governments play a central role in regulation and investment. International organizations, like the UN and World Bank, fund water projects and set development goals. NGOs such as WaterAid focus on grassroots access and sanitation in vulnerable communities. Private companies may manage water services or provide technological solutions, but their involvement raises concerns around affordability and access. Local communities are essential, especially when it comes to maintenance and equitable distribution. Successful water management depends on balancing these perspectives and ensuring that no group is left behind. Finally, integrated water resource management offers a comprehensive approach to water security. IWRM considers the full range of water uses and the needs of different sectors, from agriculture to energy to ecosystems. The Mekong River Commission is a model of IWRM, where multiple countries collaborate to manage the river basin, balancing competing needs for water. However, implementing IWRM can be challenging, especially in politically sensitive areas. For example, the Colorado River Basin, shared by the USA and Mexico, faces conflicts over water allocation due to prolonged drought and overuse. Despite the 1922 Colorado River Compact, states continue to clash over how much water each can consume, leading to ongoing negotiations. Thank you for watching. If you found this video helpful, please give it a thumbs up, subscribe for more content on all A-level geography topics, and check out the related videos to deepen your understanding of global water issues. See you in the next video.